So friends, now we are into our week 11 second lecture as part of risk conscious operation management of complex engineering system. We are discussing maintenance management, risk conscious maintenance management, and here before we talk about the risk conscious maintenance management, we will be talking about, or we will be discussing and seeing what is the role of risk informed. Risk informed is in nutshell, probabilistic risk assessment models are available, and now it is a worldwide accepted acceptance is there, and now its applications in so in regulatory domain, mostly in regulatory domain it is called risk informed decisions, and in engineering domain or in plant perspective like risk based inspection. So these two models are there, and my book on risk based engineering it brings out all these aspects. So this particular risk conscious operation management is from my second book, where the focus was in operations management. Now what are the fundamentals? Okay, it is accepted that when I am putting the word conscious, that means I am bringing it not only consciousness, I am bringing in the component of human, and the human factor is cognition, consciousness, and conscience. Because now we are more discussing about safety risk and security risk. So that way it has got a larger canvas to capture both risk and reliability with this connotation of RC. And then risk matrix. So the major matrix is core damage frequency. In the nuclear parlance, the core damage frequency is used, but risk can be discussed at any level. You have to define your hazard, and then a risk component, performance of the plant, and then risk perspective enters there. So definition might change, but then the risk is the primary matrix that characterizes whether it is a larger release frequency or core damage frequency. It is the consequences in the public domain at the level 3 of PRA. So that is not a question. We should be able to come to risk because it is a risk conscious. So all the parameters will drive down from that perspective. Now plant specific data. I mean, for risk conscious maintenance management, it is better because this is the only way we can embed in plant culture, because we are talking about risk consciousness. So that means whatever data we use for risk conscious maintenance management should be plant specific to the extent possible. If the plant has operated for 10 years, then we must be having enough data because it is a periodic activity. For certain component we do monthly, quarterly, or maybe weekly also. So we will have a lot of data. But if there are no data available, then we can have it from a qualitative matrix. But data should be plant specific data should be there based on expert opinion if we want to go into qualitative domain. And postulation implementation of risk conscious culture, as I told. Now the data itself will tell us. This is one of the method. If I collect the data from the plant, why failures are occurring, in certain domain for certain equipment or certain aspects or certain condition. It could be an area which is not, just I am giving an example, where air conditioning is not proper. So operator must be feeling uneasy all through, or the area is very hot. It happens in area, you can't help it. But now the trend is, it is at least the attempt is made to create a air conditioned cabin, so that operator can be in the ground benign, 50 degrees centigrade, 50% humidity and 22 degrees centigrade temperature, and he does his job, data logging analysis properly actually. Control room, of course, these conditions are there, and objective is risk reduction or maintenance primarily, and then reliability improvement. So here intuitively we come across two objective functions, that is risk reduction and reliability or plant throughput improvement. So we will discuss how multi-objective approach works here. And then configuration management is a way, policy changes, these things they characterize my RCMM activity. Then quantified margins. I mean, in RCMM, our wish list is quantified margin, but suppose if it is not quantified margins are available, and of course it will not be available in all the aspects, so we have to use expert opinion there also. I have told you fuzzy logic and all that, and because defensive depth requires us to have a very good margin is one of the key figure in even defensive depth. Though in those days, in the era of systems where they were being developed, it was kept as a term which is based on the judgment, but now we are having a quantitative matrix available. If the data is available, we can do it. Metrics for evaluation, the surveillance test interval maintenance part of evaluation will be considered. So here one example will be presented, so that we get the right perspective ki what is this methodology and what it can do and how we can get benefited. So as I told you, risk conscious culture, how I'll develop based on my data that is available, and then what are the standard metrics that are available in a national document, international document, and from there I would try to see which are the strength of my plant and which are a small area weaknesses of my plant, and I'll work on my risk conscious culture. And that doesn't start into operation, it starts right when the designs are going on, when equipments are being built, whether there will be a sufficient space for maintenance, what are the tools required, what kind of condition the maintenance staff will feel, and those your postulated scenarios, they become part of the design, and then finally percolate down to operation, maintenance, and refurbishment. So role of RCA, it can never be overemphasized. Root cause analysis, though initially it might look an expensive proposition, or expertise is also required, because if you want to do a proper root cause analysis, then we have to have a lot of data, information, models, methods, and all that. But in long run, same problem which was there in one pump, and if we understand the root cause to the human level, then we can reflect it in tens or 15s of pump, whether they are also, and you will not be surprised that the same cause was there for all the pumps. If the crew was same, or same tools or systems was being used, and then quality QA is there for any system. So in all these tasks that I am talking about, there are challenges to bring to work on the systems so that we get the expected benefit. Quality assurance program, we should have a dedicated quality assurance program in terms of quality of the procedures. They are reviewed, they are being validated, they are meeting the status of as built and as operated plant, and of course the human related issues. So, and then there can be a checklist derived from either international document or national guides, or even at the plant level the work can start. And adoption of PRA for PRA model, PRA model, for one simple reason, PRA was done some 3 years ago, and now if you use the same PRA, we lose the experience of last 3 years. So for any application, PRA model has to be adopted. Some modification was done in the system, or some policy changes were done in the system. So those things will form part of this. And then maintenance procedure, it is one special item: maintenance procedure in operation, normal operation, and maintenance procedure in emergency condition. 2 categories of procedure should be there. So, and if you do those procedure, you might also get the symptoms. Certain thing in emergency, they should be required, and they should be available at the site itself. Many times when we do the procedural analysis, we understand the limitation and strength of that thing, and whatever limitations are there, they have to be addressed. So for emergency operation, you don't have time. So certain tools, fixtures, methods, wall strips, they should be available in the area. So emergency and normal operation. And then available time window. For every task there should be a time window. If I change the equipment or configuration I have changed, same time window will not be available. So the time window should be updated for every task, and maintenance staff should be told for emergency this time window is this much, and for normal operation this is this much. So these kind of challenges are there, and we have to bring it out in many of them there. I am not saying they are not there at all. They are there directly or indirectly, but in a formal way, if we want to implement this conscious operation management system, these things are the prerequisites. And then technical specification optimization. This is one of the technical specifications are derived based on the traditional approach, deterministic method. Even today, the state of art is they are derived from the technical specification, where conservatism is the principle, then defense in depth is the principle, and there are many things. So conservatism itself, if we take, now we have data. So can that margin be reduced by presenting the data, and again going for risk informed decision only. So these kind of things, so whatever limitations are there, deterministic approach, that can be compensated or they can be managed through probabilistic risk assessment methods if the data and models are available. And I think we are in this era where PRA is becoming a part and parcel of regulation, operation and maintenance. So, and major risk informed based on applications are, so if I have to limit in technical specification only, I told you technical specification is the document which everyone has to follow in the plant. If it says for this condition plant should be shut down, it should be shut down. If it says plant should be power should be derated, it should be derated. In total verbatim manner, the thing should be respected. So what are the major component of technical specification? It's a big document, but allowable outage time, how much time a equipment can be allowed to remain under maintenance. So maintenance terminology has come. Surveillance and test maintenance schedule. What should be, because standby system, often many systems they may not operate all through the life of the plant, like emergency core cooling system. So this should be tested periodically. So surveillance test estimation, that schedule, it comes from technical specification. And then risk monitoring approach to maintenance scheduling. There is a respect for tech spec. So when we decide a schedule, we see that tech spec is not getting violated anywhere. This is one broad benchmark that has to meet. And then optimization of maintenance condition in emergency operating procedures. I just mentioned in the previous slide. Safety parameter setting, calibration checks. If any drift is there, they are corrected on instrumentation. Of course, it is related to instrumentation. And stipulation of regulatory compliance. And there are separate clause where the regulatory oversight is implemented to ensure that the compliances are in the place. So these are the scope of technical specification where maintenance is related directly or indirectly. But then so far we had discussed only three breakdown: periodic and preventive maintenance. But if you see the evolving scenario, and if you want to get the updated state of the art and R&D, you will see that condition monitoring I have discussed. This is being implemented, but it is at very limited level for very special components like shutdown emergency pumps, or if suppose if the pumps are required for higher reliability of the plant, then it will be there. So there should be a matrix where it should be divided, and probably risk assessment is the best metric that is available, where this concept can be extended to across the plant actually. And then we have now, since reliability methods were there, I just mentioned reliability, availability, maintainability and safety. So RAMPS it is called. So those methods were available. So this reliability maintenance, it start from quality level and it can be a quantitative level also. At qualitative level, there are some parts like reliability task force should be formed, and they should review the mode of failure and correct the maintenance efforts periodically, and then the failures are more means in qualitative manner. Then we have to enhance our maintenance activity. So it can be at qualitative or quantitative level, but the scope of these things is at the system and plant level. But condition monitoring remained at the equipment level only. And then model, reliability model of the system is required, and then generic, anywhere you can apply it, industry and plant specific level, and then state of the art is matured at qualitative level. Quantitative level, the data are being used slowly, but the next one is the prognostics and health management. This is, I would say, this technique is to a great extent it is in the R&D domain, but on electronics it is really being used, but by and large PHM application, only one area for PHM application, that is remaining useful life estimation, and especially for bearing. It has become the most popular subject, and for, of course, passive structure health management also. So it is there in the field, but R&D support is a must even today if you want to improve upon these methods, And then we have risk-informed, risk-based method. Yes, PRA document is available, and then it is at the plant scope level, and then applications are promising approach for risk and reduction, and I would say even availability improvement, that is reliability. Open literature shows becoming part of the risk-based applications. And risk-conscious maintenance management, this is very relatively, my book was published somewhere in 2023, and probably if we integrate the human element, we might get a like top icing on the cake actually when we use it. And of course, I would admit that further R&D is required for implementation of this approach. Okay, then what is the role of probabilistic risk assessment and maintenance? How we can relate them? PRA is at the core of RCM, because whatever I do, there I use the plant data. That means data is coming from the plant. It is reflecting the plant characteristic. Then I do the risk modeling. So that means it is getting converted into risk of failure or probability of failure, and it is joining at the faulty level or at the initiating event level. So PRA is a part and parcel of maintenance management, risk conscious maintenance management. And the metrics could be core damage frequency. LERF we will not discuss now because it is a level 2. That means once the hazard percolate down into the maintenance containment, then only this comes into the picture. So we will remain risk per year, that is core damage frequency for nuclear plant. For other plants, as I told you, we can take our hazard and you can have a risk statement. So what are the type of data? One is frequency of failure, like frequency of power failure becomes an initiating event. Frequency of a component failure, if you multiply with the failure rate, if it is a mission time related component, then if it is a demand failure, then QD, our PRA we call QD, demand related failure, or normally it is characterized as unavailability, because failure was not able to detect immediately. It happened in the passive mode. So half lambda t is one assumption which is made for these failures, and we get the unavailability statement from here. And then mission failure probability, that is continuously operating system. If my process pumps are operating continuously, I am gaining the reliability of the plant. If the pump fails, my reliability gets disrupted. That's why condition monitoring and so many activity methods are there to improve the reliability. Human failure probability is at the core of risk conscious management. So I don't mind repeating the sentence that even today the human factor has been major contributing factor to the accidents. If you see all across the spectrum, whether it is aviation, whether it is railway, whether it is a coal mines or space systems. So everywhere if you see this data is available in open domain, and fault-free inventory form part of the risk modeling. Okay. Now this is one IIA model that they have given here, that we have a risk as a target, and but then we have data, raw data available with us, and then we have test and maintenance, human unavailability, rated availability, and then through PRA model we do prioritization and revisit maintenance requirements, and that's how we touch the risk targets. So data, mission failure, human failure I have given in the previous slide, and then finally we have a closed loop where we draw the benefit of structuring the risk conscious maintenance management. Okay, now let us focus on data, and suppose if PRA model is not available, how we will prioritize our data, So that common cause failure is one of the big no-no that should happen in the plant, because it kills all the redundancy built into the system. And if common cause failure is induced by human, then it should be taken the highest priority, because we are talking about risk conscious maintenance management. Then second common, I think you must be knowing, yeah, I have given the abbreviation. Okay, so common cause failure is O&M, operation and environmental. So if that happens, some smoke, and it leads to similar identical equipment, redundant equipment failure, or flooding in the area, it leads to all the equipment failure. And that's why to handle the common cause failure, if there are 3 equipment which are redundant, one will be put at different location and 2 will be put at different location, or all the 3 might be put at different location, whatever allowed. We can do only at design stage, but if the plant is designed, this option is very limited. Then the common cause failure HS, that is software component failure. You know that this is the one of the big issue, that whether the safety critical system can be designed and can have software on 3 or 4 redundant channels. And so the question is, if there is a software bug, then all the channels will behave same and it can bring the system to shut down. So as on today, the state of the art is, if we are using a digital system, there should be a hardware system, relay-based system, solid state system to compensate the safety issues that might crop up with the software failure. And then risk failure leading to a risk event. I mentioned you, even if there is some accident in the plant is unavailable. So availability, reliability is not the case. Even risk can add a huge component of unavailability, or the plant got written off. That means there is no throughput. So segregating them in a box is not a good idea. And okay, and then dominant risk conscious fraction. Very important thing is being discussed here. If there is a root cause, and its fraction is more if we go, if we analyze different system, 10-15 analysis, and we found that in out of 15, 12 were related to this root cause only on a pump. So we got a very big fraction, then it is a risk significant. If it is risk significant, then it becomes very important, and safety margin related thing. So even I didn't have a plant, which my plant brings it in a systematic and rational manner at the PRA level, I could do at least 80% of my job actually, of prioritization and all that. And here we have risk metric, PSA, safety prioritization, interpretation, very well made sensitivity analysis. That means I am able to see the impact without any brainstorming or anything, and I can see the impact on the plant, where human factor, plant design, all those things, and then monitoring, and I can work out so for system, for feedback, monitoring and all that. So these two are the approaches where maintenance can use this data and prioritize their maintenance activity. Okay. So one of the very important tool which could become a very effective way to understand the maintenance and to evaluate the impact of failure and how it affects on the risk. So this is a risk monitor. Okay. Typically, risk increase or decrease has been shown here because some activities are going on. Don't go by this because this is for visualization, just to have, but the risk increase by a very small fraction or decreases for a very small section. Otherwise, it remains at the reference level. If it is accident, then only. So here it is meant for demonstration, this small thing. So real-time risk reduction. Now there is a situation whether I should, some plant is operating and 1 hour is required for maintenance. Can I take out that equipment out of service for maintenance? If I go by my technical specification, it will give some crisp or stipulations. But if it is allowed that my risk informed culture is available with my plant, I remove it and I'll see there is no risk reduction. There is no risk reduction. So can I put the second question whether I can take out? As on today, we are using the traditional methods, we cannot do it. Whatever written in tech spec has to follow. But this provides a additional window, and wherever risk informed approaches are implemented as part of regulation for operation and all, it can. So if suppose I was testing certain system and by chance because of some problem, big problem, one pump was to be replaced. So it took more time. Can I start my plant with that system? Is taking hardly half an hour remaining or 1 hour or 2 hour remaining. So can I start my plant? So the risk monitor becomes a very, it allows you to visualize the things actually, you know. So more risk assessment tool and more benefits. So in this lecture we have discussed PRA, its role, risk informed, risk based and prioritization of SSCs, and risk monitor in online maintenance and all, how it helps. I just mentioned in the previous slide. And yeah, so this is our you can say lecture on PRA and risk, and now we will move on to our next lecture, and that is on framework and implementation.